Okay. Part one, we're going to consider coevolution. Overall, these are results of studies which I'd say the ideas in these papers have been influential in other people's applications. And perhaps there's take-home messages for things which you would like to try to do. Okay. So first we'll consider coevolution. So coevolution, we've talked about using a GA to solve an optimization problem. You can still use coevolution in this framework, but one standard motivation behind coevolution is there's problems which you might want to try to solve where you can't clearly model with the pure fitness function approach. What's the characteristic here? Somehow the fitness doesn't exist as an independent function. You know, you can imagine you're trying to solve a traveling salesman problem. You give me the problem. The fitness function is independent to the members of the population. If I tell you that, for instance, you're playing a game like backgammon, it's unclear how to define a fitness function for backgammon. I mean, using game theory, you could probably define a very, there does exist an optimal backgammon player, but having access to such a thing we wouldn't have, and if you had it, then you wouldn't need to evolve a good player probably, and so forth. But in general, game playing is a good example. It's hard to know what the fitness of your player is, but you can define it relative to a fitness of programs that play this game. Okay. I'm not going to. I'm not an expert on the natural world in any sense, so I'm not going to overwhelmingly try to talk about coevolution of nature, but often coevolution of nature is defined in the following way. Reciprocally introduced change between two or more species or populations. Kind of the prototypical example is some sort of arms race between species. So one trait in one species evolved in response to another trait in another species, which was evolved in response to the first trait, and so forth. So you have these rabbits that like to sleep on rocks in the sun and they're colored purple, and you have these foxes which are kind of slow and they're scared of rocks. And you can imagine that, well, as the foxes start to not become scared of rocks, well then the rabbits better evolve some tendency to not sleep on rocks in the sun, and then the foxes can see very well, but they can sure see purple. I mean, this is an unrealistic example, but you can imagine, just like we have some arms race in our own society, you can imagine some arms race where two species are interlocked, each improving in response to the other. A classic example is, not a classic example, but a more complicated example is coevolution isn't just predator and prey, but there's often more complicated relationships going on. So butterflies have evolved in combination with some plants so that the caterpillars detoxify the defensive chemicals in the leaves. Butterflies can recognize the appropriate leaf types and shapes. Plants at the same time have evolved nectaries which the ants like, which attract caterpillars. Some other plants evolve structures that look like butterfly eggs because these plants don't want butterflies, whereas this plant wanted a butterfly. So the different species interact in different ways. Okay, a classic GA experiment revolved around Prisoner's dilemma, study of coevolution. Who here is familiar with the Prisoner's dilemma? Raise your hand if you've never heard of the Prisoner's dilemma. Okay. Prisoner's dilemma is the following idea. It's from 57. I'll just read this to you. Two suspects are taken into custody and separated. The district attorney says it's certain that they're both guilty of a crime, but he doesn't have evidence to convict them in trial. So they talk to each prisoner independently. He points out to each prisoner, so this is happening independently, that you can confess the crime that we're sure that you've done or not confess. Okay? The situation is the following. If they both don't confess, then probably they can't fully charge them. They're not going to fully charge them, and so they only get a lighter sentence. Okay? However, if one of them confesses on their partner, then they'll cut a deal with that person and convict the other person for the full crime. That's great. But however, for instance, if they both confess, they end up having the evidence against both of them, then they can both be prosecuted for this most severe crime. So I think this might have been when this particular two-player game was first observed in 57. I could be wrong. This two-player game could be earlier. But we can describe this as a game in the following sense. What we do is we look at there's two individuals. And forget the previous notation of confess and because it confuses with cooperative and defect. The way a two-player game works is the following. Player A chooses some action, for instance, cooperate or defect. Player B chooses some action, cooperate or defect, either in communication or not in communication with one another. They then reveal what they've chosen to do. Perhaps they reveal that they both cooperate. Perhaps they both reveal that they have defected. So in the story, if they both cooperate, that's like they're cooperating with one another, so they don't tell anything to the police. If they don't tell anything to the police, you imagine they win a score, they receive some utility. They both they cooperate with one another. They each get 3 points. So as individuals, they're not so unhappy. However, suppose one of them goes ahead and defects, i.e. talks to the police, while the other one doesn't. Well, the person who turned out to be a traitor, they do quite well. They get let off, and the other person is sentence law, so they receive 5 utility, and the other person will receive 0. It's exactly the opposite for the other scenario. However, if they both defect, they only receive 1 point each. So people often believe that this can explain a variety of situations in society. For instance, arms races. Okay, so you can imagine two nations are interlocked, and they have a choice of either building up their military or not. Suppose neither of them build up their military. Well, that's pretty good for both of them, because then their economies can flourish. They don't have the strain of spending money on military, and it reduces the chance of a conflict. Suppose, on the other hand, maybe this is nuclear weapons, for instance. Suppose, on the other hand, one country builds nuclear weapons and the other country doesn't. Same thing as conflict. Well, the country that's perhaps spent more on defense or offense or on nuclear weapons can now kind of pressure the other country, because behind their actions there's always the threat that they might act on them. And so they can get, advantageous trade agreements, some other side state that both of them would like to have more influence in. They can basically go in and the other country can't do anything about it. So that's a win for that country. However, suppose both of them continue to build up their defenses. They both build nuclear weapons. Well, now neither of them get that advantage that, oh yes, I can bully the other. They're both interlocked, and now they're spending, for instance, more money on their economy, and there's this potential risk of a war which will be increased, which will be good for neither of them. So they both lose if they both build. So arms race, tragedy of the commons. There's some sort of resource which people can share in a village. People can try to share it and not exploit the resource. Well, if they do that, they do well. If one person starts exploiting the resource, it destroys it for the other people. If everybody tries to exploit it, nobody. Okay, I didn't do that so clearly. Another maybe classic example is your coursework. All of you could get together and say, we're given a lot of coursework assignments. These are a lot of effort. Maybe if we just spent a little less time on this assignment, all our scores would look pretty similar to one another, and it would be hard for the lecturer to fail all of us. Of course, there's always one in the class, one who goes, I'm good. I need to move on to the next level. Let the rest of them do what they will. I'll work out really hard. So everybody thinks that they have this agreement that, we're not going to do very hard. It's like this one person's done really, really well, and it just makes those other people look worse. But then what usually happens is, everybody, okay, we better get this assignment done. Okay, I'll work really hard. Okay, you work really hard. Everybody works really hard, and because they don't want to be the one left out and spend a lot of time, and you all have great scores, but nobody really stands out, and so you don't do as well as if you all just decided to not work very hard. So.
That's the message that you should.
Well, take from it what you will and see what happens. That's why it's called a dilemma. Okay, so because I'm curious and I like experiments on it, and make sure that you understand the setup before Axelrod does it. I know I'm moving slowly, but such is life. Let's play Prisoner's Dilemma. Okay. So what I want you to do now. So the way what we'll do it is we'll do a couple of practice rounds to make sure you understand what's going on. But I want you to break up in groups of two where you'll play Prisoner's Dilemma against one another, and then you'll change to another group of two, and so forth. And then I'm going to see who wins. So let me get in twos and I'll explain further. Okay? So please organize yourself into groups of 2. If you're not, if you're not in a group of 2, raise your hand.
So imagine those are years that the person gets.
We do have an odd number this year, so can I persuade you to team up with somebody that you'll be what? No. Team up. So rather than acting as an individual, you and this other person will always act as a group together.
Yeah.
So.
Yeah, he's one of the
No, you're good. Okay, so what we're going to do first is a practice round or 2 to make sure you understand what's going on, okay? So you'll each take a piece of paper. Maybe you discuss beforehand, maybe you don't discuss beforehand. And you go ahead and you decide whether you're going to cooperate or defect. You show each other what you did. So maybe one of you will say cooperate, maybe the other one of you will say defect, and you each score individually. Where your goal is to get, I forgot to bring a prize, but it's at the end to get the most points as an individual as possible. Okay? So why don't you go ahead and do this now and play one game against the person behind you. So you reveal your actions simultaneously, and then you see how many points you get.
I think the sequential
iterations,
it's
different.
That is a different game, isn't
Yes,
it?
Definitely. Repeated prisoner's dilemma is not the same as prisoner's dilemma. I understand, but I only do.
It's a good subject game, though. It's really interesting.
As soon as you've played one round, raise your hand. Okay, one round's been played. Wait a moment. Okay, has everybody played one round yet?
Yeah.
Do you have any questions?
Okay,
Okay, that first round doesn't count. Okay? Now that you understand what's going on, pause. Now I want you to play, I guess we have a limited amount of time. Play, say, 5 rounds against your partner you've chosen. And then after you've played your 5 rounds, keep track of your score, find somebody else in the room to play against, and we're going to do this 3 times, and we're going to see which of you is good at this game or not. In my experience, I find that students who do well in Prisoner's Dilemma are usually, they do pretty well on the exam. We'll see if they have so I encourage you to win, because there seems to be a strong correlation.
But the goal is only to
Yeah. What?
Is there a learning?
Is there what?
A learning.
A running?
Learning.
Learning.
Then we look at the first one.
Yeah, you show what happens, and then you look at the first one, and then you make a decision how to play the next one, and so forth. Yeah, you get to see. No, you don't play 5 arbitrarily. You play 1, look, see what happens, score. Play a second one, look and see what happens, and score. Play 5 rounds. When you've played 5 rounds, you then find somebody else to switch. If you have a question, raise your hand. Player A gets the player B. Player B gets 3. Player A gets 5, and player B
I see how cool you are.
Higher score. Higher score is better. You can almost get the highest score.
Yeah.
It's not fair, I have to so points I got 19.
At the end of this game, you're going to get that many years of your life back on your health and wealth.
Because I all by
I mean, that's one way you can phrase it. It's nothing to do it's not your it's years in prison. But it's not I'm going to find out how much you do. I'm going to see the right class. 15 years old, that's and I'll see how well each of them does. And you have some
Ready when you are?
So are you keeping score?
Oh yeah, I'll keep scoring.
Okay.
Ready? Cooperate. So I go to the police, you go to prison. Oh, we do it. No, we do it. Okay, let's start again. We should define the parameters. So we had it saying cooperate was what talks to the police.
Oh, okay.
Defect was don't talk to the police.
Like cooperating with the other one.
Oh, so in which case you both got the same thing. So you both got the same thing.
No, cooperating with the other player is not cooperating with the police.
Oh, I see. So I got so you get
The other player is
Oh, I see. Oh, okay. Then we have to go around. So 3 points each. And I'll go with your way. So if I just change that one to defect. So
now defect
is goes to the police. I'll go to your okay, alright, so defect is goes to the police. Okay, so I think you know what we're going to Okay, right, I don't think we need to fight. So we've both got the same number of points, so 3 both times. Okay, fine.
You want to try something? One round at a time.
It's called a Nash Equilibrium. It's called the Nash Equilibrium. When you reach that point where there's a really good film actually, Russell Crowe, about how game theory yeah, it's a Beautiful Mind. It's really good. Watch it, really good. It's all about this kind of how this kind of theory came about.
Sorry, Beautiful Mind.
Yeah, exactly. Yeah. Mark, have you seen A Beautiful Mind? Yeah. Well, that scene when you're in the bar with William would be a good fine one. Yeah, sure. Okay, hang on, before we start, which for you is defect, go to the police or cooperate with the police? How do we do it?
Just do it according to the table. Cooperate means cooperate with one another, not with the police.
Right.
That's the way the story works. That's why
Okay.
this presentation is confusing, but it is the standard.
strategy will be. Okay, yeah.
Direction.
Yeah. That's what I meant. You got me confused, that was all.
Yeah, forget about the police. Unfortunately, that's just what I'm told, but this doesn't correspond to
Okay, so let's play one round.
Okay.
Ready?
Try to maximize the
Ready? So the maximum is to play with the strategy like a team.
Alright, okay. So we both agree to cooperate. Right.
So we have 9 points.
Has everybody played 3 rounds yet?
So yeah, that's cool.
So I assume you've played 3 rounds. How many people have played 3 rounds already? You switched and played with a different set of people. So everybody's done 3 rounds, or is there somebody still left playing?
Well, we're still on the 3rd round.
Okay. Yeah, 3 different people. But you need to find somebody to play against. You may have missed your opportunity.
We need another one. Mike.
Oh, okay. I've gone through already. Okay.
With another person.
Yeah. Sorry.
Play 5 times with one person on a switch one and we go last one.
Other side.
You're not winning turn.
Oh wait.
Okay, so for those of you who have finished, total up your score for your 15 individual games.
Let's go to cooperation.
Okay, yeah,
Because I am, I don't
Okay, has everybody played 15 rounds now?
Yeah.
Okay, so presumably it's fairly easy to get 45. So who here has 45 or more as their score? Right, because you could have just cooperated all the time. The guy was 45. So you have more.
Every single one was corporate.
So what's your score?
I don't know. I kind of lost count.
Oh.
So
Okay.
it's a bit confusing.
Okay. Well, sum your score up.
Okay, I'll try. Okay, so
You'll try to sum up your score. You have to be able to sum scores in this class. You can't sum 15. Okay, who has a score of 40 or more?
it should be affected on the top. Or I didn't we?
Who has a score of 35 or more?
1, 2, 3. Okay, so.
Okay, what's your score? 40.
15,
40. You have a 40. Are there any other scores of 40?
42.
You both have 42. So you have two
35,
42s.
45.
Anybody with a score between 35 and 39?
37.
37. Any other scores in that range?
I've got 45.
40. You have 45?
Yes.
No. Anybody, what's the next, anybody with a score between 30 and 35?
34.
34. Okay. Anybody with a score between 25 and 30? Okay. 30? 29? 28? 27? 26?
Wait, I had
2
39.
scores? 1 score, 26, 25? Okay, between 20 and 25. Okay. So what's your score? 23.
Yeah.
Between, what's your score? 24. 24. Anybody below 20? Nobody else. Somehow this didn't add up to the number of people in the class. You know, I can't put everybody in the playground. Well, 45 is not bad. That's quite good. I'm surprised you all didn't get 45 because, you know, if you wanted to maximize your utility, all you had to do was cooperate all the time. Yes.
Counterpoint, human nature.
Yes, that's the problem.
Nice.
Why is it hard to get this score of 45, even though it's certainly obtainable if you just cooperated with one another?
Well, because I've always had an incentive to defect, right? Like if I know that the other one will always cooperate, then at least in the last round, I should actually defect, right?
Yes. What was it? Yeah, so this is the problem. This is why it's a dilemma.
But
yes.
Sorry. Can I just
please?
I thought there might also be local optima involved, because if you're around people who are particularly predisposed to cooperate, then you're likely to get a better score.
Yes. So right. You know, once you're playing with real people and you're playing multiple games and you can choose your opponent, it suddenly becomes more kind of complicated than the one-shot variant which game theory is developed for, which you note. But the idea in game theory, which we're just going to do lightly as we were doing so far to kind of motivate what Axelrod did. There's a lot of work in evolutionary game theory, but game theories was developed as a way to explain optimal strategy and explain what people do in two-person interactions. Von Neumann and Morgenstern, and I guess they developed the theory of zero-sum games. There's previously, maybe say by Banach, I can't remember, there's somebody else around the turn of the century. I think they weren't the first to define games. Nash, who you're probably quite familiar with, one of the things that he came up with was this concept of Nash Equilibrium. And the idea is that for a two-player game, if you make certain assumptions about what a game is, that you get utility for each play, each player wants to act rationally. The Nash Equilibrium, which not every two-player game has, is a place where what you kind of expect is the outcome of a single round. Let's understand what the Nash Equilibrium is. So a Nash Equilibrium is a pair of actions such that no player can benefit from the deviation given the other player's actions. So let's try to go back and apply it to this previous game. So an equilibrium position, i.e. a strategy chosen, a strategy pair is an equilibrium if no player can benefit if the other player individually defects. So let's see if cooperation, which overall generates the most utility in the system, let's see if that's an equilibrium. Is cooperation an equilibrium? No, because either this player A, player B would benefit by defecting. Likewise, player A would benefit by defecting, but just one of them being able to benefit from defecting by changing their strategy means that this isn't an equilibrium strategy. Let's say, is this an equilibrium position? If we look at this game, this position, player A does not benefit by defect by changing strategy because his utility would go down. However, player B benefits. So this likewise isn't an equilibrium. If we look at this table, however, this is an equilibrium position because neither player benefits by changing their action. Suppose player A, considered independently, suppose player A decides to change their action, that's this player, they change their action to this action, well then they get 0 points, so they don't benefit. And it's the same situation for player B if they change their action here. So the predicted action is that if you play this game, you're going to play it one time, there's no learning, there's nothing else going on, you're in this situation, the rational outcome to expect is that both people do this because they're each doing something that's going to optimize their outcome. And this is why this particular game is a dilemma. This is a story of a one-shot game, and this is the action which game theory suggests is the outcome given the assumptions. It's a mathematical theory. The question with any mathematical theory is, of course, how well it fits reality. Axelrod was a sociologist in 1987, wrote a very influential paper. If a lot of situations in society actually correspond to prisoners' dilemmas, it doesn't seem in every case that in a repeated version of this game that people are always choosing defect. So he wanted to explore the question of how it's possible that societally that we're not always defecting, and this is discussed in a series of experiments, and it's connected to genetic algorithms. I see that I've hit the time limit, but since there's not, let's just do 2 more slides so we at least get game theory done. I'll feel terrible to make sure that if you don't understand, but feel free to leave, and I won't judge you very harshly. Okay, let's figure out where the Nash equilibrium in this game table, if any. So for a 2-player game, it doesn't have to have a Nash equilibrium, and it can have more than one Nash equilibrium. So using the definition on the following page, are there any Nash equilibrium in this table? If so, what are they? Volunteer from the audience.
Choosing the same option?
Yeah, either Bach or Stravinsky is an option because suppose you choose Bach, player A will not improve by changing. Player B will not improve by changing. So this is a Nash equilibrium. What about Bach, Stravinsky? Well, if this player changes, it improves their option, so it's not a Nash equilibrium. Same argument goes from here for symmetry. So these are the Nash equilibrium for the Bach-Stravinsky game. The story is, maybe you want to go on a date with somebody, and you're a Bach lover, they're a Stravinsky lover. And the Royal Festival Hall is at Bach, and Stravinsky is at Wigmore, and maybe you prefer Bach, but if
you go and listen to to Bach, and they go listen to Stravinsky. You know, well, you hear your music, but you don't have your fun date. So either one is potentially Nash equilibrium, though certainly player A has a preference for one and player B has a preference for the other. Another thing, you both want to go on a date again, you both like Mozart a bit more than you like Mahler. What are the Nash equilibrium here?
There's no tickets left.
What?
There are no tickets left for Mozart.
No, there are plenty of tickets. So, just to point out, Nash equilibrium, it's not enough to... both of these are Nash equilibrium under the definition of Nash equilibrium because neither, if you both choose Mozart, there's no reason for either of you to change. Likewise, if you both choose the action Mahler, there's no reason for either of you to change. But in terms of being a predictive theory, you know, it'll be rational for you to both choose Mozart. So I'm just pointing out, if you have two Nash equilibrium, you know, it doesn't predict. It's not predictive in what you're going to do. You have to maybe add some assumptions, and it's actually quite complicated. This is an easy case to decide what might go on, but otherwise it's not so clear. Okay. Let's do any Nash equilibrium in this game. Dove Hawk. So here's the idea that you know, this is another one. These all have military metaphors too, but so you know, Dove and Hawk are fighting approach to food, and you know, you can have dovish behavior or hawkish behavior. So the idea is that you know, there's some food on the ground. You know, you can sit there and both share the food. It resembles the prisoner's dilemma, but if you check carefully, this isn't the same as the prisoner's dilemma. Otherwise, so the two doves share the food. Otherwise, a dove and a hawk come by, and well, the hawk scares away the dove, and the hawk gets all of the food, so it gets more utility, and the dove lives to eat another day. Parallel situation here. You can imagine the two hawks land for the food. They don't share the food at all. They fight one another till they're bloody, and they don't live another day. So they both lose. Are there any Nash equilibrium in this scenario? If so, what?
There's not, because if you are both at 3-3 at dove, then if you decide.
So 3-3 is not a Nash equilibrium because if we look, player A would benefit by becoming a hawk. Likewise, player B would benefit by exhibiting hawkish behavior. So 3-3 is not a Nash equilibrium.
4-1.
What about 4-1? Yes. So these are both Nash equilibrium because player A does not benefit by changing his hawkish behavior to become a dove. Likewise, player B does not benefit from changing their dovish behavior from player A. And then we can check that either player benefits by changing this position, so that's not a Nash equilibrium. We'll do the final one, then we'll discuss Axelrod next week. And so, you know, it's completely unclear which of these Nash equilibrium would be chosen. What about in this game, rock, scissors, paper? You've played this as a child or an adult. I put out rock. Rock crushes scissors, so rock has 1 point, scissors has 0. Loses a point. Rock, neither of them make any points. If I play rock and you play paper, paper beats the rock, so it gets 1, and so forth. Any Nash equilibrium here?
No.
Yeah, you can go ahead and check in any position you are. there's always one player who's either tied or losing. The player who's tied or losing can always change to a winning position, so therefore there's no Nash equilibrium anywhere. The results then proven by Nash was that if you allow randomized actions, i.e. you play each action with some probability, then there always exists at least one Nash equilibrium. So here, Nash equilibrium is you play each rock, scissors, or paper with 1/3 probability. And then in this situation, if you play them 1/3 probability each, you're likely to have exactly 0 score. There's no improvement for changing that away from probabilities 1/3, 1/3, because if you change it, the other player can take advantage. Okay, we'll discuss Axelrod and game theory next week or the following week. Have a good weekend.